Okay, so in day 2, part 2, we're going to take a look at dynamic programming. Okay, so dynamic programming is a methodology for solving some complex problem by breaking it down into simpler subproblems and exhaustively solving all of the possible subproblems. The main difference between dynamic programming and just ordinary top-down programming or recursive programming is that in dynamic programming, we're careful not to resolve subproblems that we already know the answer to. And we do this by what's called memoizing solutions that we've already computed. Memoizing is not a misspelling. The idea is that we're going to create a memo of each simple subproblem that we've already solved. So this was originated by a fellow named Richard Bellman at Rand Corp, which was a defense, well, still is, a defense contractor in the United States. And at the time, according to Richard Bellman anyway, the Secretary of Defense was from an industrial background and had great suspicion of scientists doing research. Apparently, this defense secretary felt that scientists doing research just meant scientists sitting in their offices wasting time. So Richard Bellman developed this term called dynamic programming, not because it really meant anything, but because it certainly sounded good to someone who was interested in efficiency and productivity. Dynamic certainly sounds exciting, and programming certainly sounds like you're working. Okay, so to motivate the notion of dynamic programming and the idea of memoizing, let's take a look at our Fibonacci number computation that we talked about earlier. This version of the Fibonacci sequence function is the same as the recursive version that we saw before, with one minor change, which is that instead of having two return statements in it, we're storing values in a variable called ret, and when we're done, we're returning the value of that ret variable. Now, we know that this works, and because the int data type in Python is arbitrary precision, this will work, in fact, for any value of n, assuming that we're willing to wait long enough and have enough memory on our machine. For example, if we look at how this function computes f of 5, well, it does that by adding f of 4 to f of 3. Computing f of 4 involves computing f of 3 plus f of 2. So you can see that this is requiring us to compute f of 3 twice. And as we get down to the next level, we'll see that we end up computing f of 2 3 times. F of 1 ends up being computed a total of 5 times in this naive recursive algorithm. So, how can we modify this algorithm to avoid computing any of these values more than one time? Well, so in order to get some value f of n, we're going to need to know f of n minus 1 and f of n minus 2. In turn, that's going to require us to know f of n minus 3, f of n minus 4, all the way down to f of 0. And it would be much better if we could compute each one of these values one time and then just look up values that we've already computed. That, in fact, is what this modified algorithm does by adding memoization into the recursion. Okay, so a dictionary is often a convenient way of setting up memoization because we can map the argument to the previously computed value using a dictionary. Initially, because we haven't computed anything yet, our dictionary is going to be empty. We will call f of n, and this time, rather than computing anything for f of n, we will test whether n is already one of the keys in our dictionary. If so, we can simply return the value that we had already computed for n. But if n is not already a key in our dictionary, then we'll do our usual recursive call. If n is 0 or 1, we'll set our ret variable to n. Otherwise, we'll set our ret variable to f of n minus 1 plus f of n minus 2. Now, here, before we return the result, is where we remember this result that we have computed. So, after computing ret, But before returning ret, we add ret as the computed value associated with the key n in our dictionary. This makes a dramatic difference in speed. It, as is said here on slide 31, turns the algorithm into a linear time algorithm rather than an exponential algorithm, which is what the naive recursion was. All right, so let's run these two examples so that we can get a feeling for the difference. Here is our naive implementation, our direct recursive implementation of the Fibonacci sequence. It's the same as the code on slide 29. And we know from experience that when we run this, as we get into larger and larger values of n, this thing slows down pretty badly. Let's run it. Okay, up through 30 is pretty quick. And then all of a sudden, things start really slowing down. And eventually, I'm going to get sick of waiting this. I'm going to hit Control-C to kill the thing off. But let's take a look now at our version using memoizing, so that when we compute f of 0, we don't have to recompute it again. When we compute f of 1, we don't have to recompute it again, etc. Here is that version of the code. Okay, so here we have our dictionary that's going to remember previously computed values. So if n is in the dictionary, we're done. Otherwise, we'll do our computation as usual, and then we'll memoize the value that we computed. Okay, now this test code actually goes way beyond the test code that I had for the naive recursive version, which slowed down badly once we got up to around 35. Let me run this. Zip. Okay, so the change from the exponential performance of the naive recursive approach to the linear performance of the memoized approach is quite dramatic. And if we take a look back at our diagram on slide 30, we can visually see why this is. Recursion is going to march its way down the left side here first. So when we compute f of 5, the first thing that happens is we first discover that that's not already memoized. So we compute f of 4, which is not memoized. We compute f of 3, f of 2, f of 1. For f of 1, we just get a number back, and we memoize what that number is. Then we need to compute f of 0. For f of 0, we just get a number back, and we memoize what that number is. F of 1 plus f of 0 gives me f of 2, which we memoize. When we then return up to finishing the computation of f of 3, we have our value for f of 2, and we know the value for f of 1. We don't have to recompute it, so we just add those up. Up here, computing f of 4, we got our value for f of 3, and we add the value that we already know for f of 2 to get f of 5. So the upshot is that all of this stuff over here, all of this stuff over here on the right side of the tree, we never have to recompute. In fact, we only recompute f of 0 once, f of 1 once, f of 2 once, f of 3, f of 4, f of 5 once. And we use memoized values and avoid recomputing all of the right-hand subtrees with the sole exception of the first f of 0. Okay, so the basic general dynamic programming methodology for discovering the solution to some problem is break that down into simpler subproblems that you solve recursively. We need to make sure that we have solved every conceivable subproblem so that we haven't missed any cases that might give us the optimal solution. Once we've solved every possible subproblem, we will simply select what the optimal solution is, and we're done. Now, in order to prevent recursion from exploding exponentially, we will add memoization, typically in Python using a dictionary, so that we don't have to recompute any value that we already have computed. In the case of the Fibonacci numbers, we converted an exponential algorithm into a linear algorithm. Often we're not going to be able to do this well, but we'll settle for getting a polynomial order algorithm. That is typically something like an n squared or n cubed algorithm. Now, I know in the past that I have said n squared is really bad and n cubed is horrifically awful. That is still true, but neither of those is anywhere nearly as bad as an exponential algorithm. However bad an order n cubed algorithm may be, it's still a very dramatic improvement over an exponential algorithm. So we simply learn to take what we can get, and if what we can get is still not good enough, then that leaves room for even further research. Okay, now for Fibonacci numbers, our task was pretty straightforward. We simply needed to compute and return the nth Fibonacci number, and we didn't have to make any decisions along the way about which direction to go or whether to buy something or sell something. A more typical dynamic programming problem usually involves maximizing or minimizing some so-called objective function, such as some cost or some income or some distance or some amount of fuel or something along those lines. And maximizing or minimizing, in turn, is going to require you to make decisions. If you're traveling from one city to another, when you come to an intersection, should you turn left or right? Should you continue straight ahead? If you're dealing with assets, should you, in order to maximize your profit, buy the asset, sell the asset, hold the asset? And what we want is a true maximum or a true minimum, not some statistically most likely good result. So what we're going to do is to try every possible decision that can be made and identify from among all those decisions which sequence of decisions leads to the best possible outcome. All right, so we're going to put together a recursive solution to our problem that checks every single possible decision. And what we need in order to prevent this from exploding exponentially is a good form of the recursive solution that allows us to memoize things efficiently so that we reduce as much as possible the need for recomputing values that we already know. And this is typically the hard part, is figuring out from among a family of recursive solutions that will, by brute force, check every possible decision, which one results in having to do the least recomputations of things. Okay, so as an example, let's take a look at the problem of rod cutting. Now, you are a manufacturing company. You buy steel reinforcing bars of some length N from some supplier, and you want to sell this rebar to your own customers in a way that will maximize your own revenue. Your customers are willing to buy rebar that have various different lengths for various different amounts of money. For example, your customers are willing to buy a 1-foot piece of rebar for $1, or a 2-foot piece of rebar for $5, or a 3-foot for $8, or a 4-foot for $9. And they're not willing to buy rebar that's longer than that, or rebar that's in half feet, or something like this. So you have to discover how to split your n-foot length of rebar that you got from your supplier into some combination of 1, 2, 3, or 4-foot pieces. To take a particular example, let's suppose that our supplier gives us 10-foot lengths of rebar. There are many, many different ways that we could cut up that 10 feet. For example, we could create 10 1-foot pieces of rebar. And we know from our customers that they'll be willing to pay us $1 for each of those 1-foot pieces. So 10 times $1 gets us a total of $10 for that way of cutting up the rebar. Or we could create 5 2-foot pieces of rebar, which we could sell for 5 times $5, getting $25. So clearly it's going to be better for us to create 5 2-foot pieces of rebar than 10 1-foot pieces of rebar. But what is the absolute optimal way? All right, well, if we try to create 3 3-foot pieces of rebar and we have 1 1-foot piece of rebar left over, that also gives us $25. What we need to do is to try every single possible pattern of ways of cutting up our rod and figure out which one of those gives us the maximum revenue. All right, so let's think about this systematically. The length of the rod that we start with is 10 feet. Each piece of rebar that we sell to a customer has to be some multiple of exactly 1 foot. So that means that there are 9 possible cuts that we might or might not make in this 10-foot piece of rebar that we have. That is, there are 512 possible permutations of rod cuts that we might make. Now, within this, there are many duplicates. For example, a 1 foot plus 2 feet plus a 5 foot gives us exactly the same revenue as a 1 foot plus a 2 foot plus a 5 foot plus another 2 foot. So we want to create a recursive algorithm that exhaustively identifies all these different permutations, but that avoids as much recomputation of the same values as possible. All right, so here is how we're going to set up our recursive solution to this problem. It's too hard to figure out where to make all of the cuts to get the optimum revenue. So what we're going to do instead is to iterate over all of the possible places where we might make the first cut, and if we can figure out the maximum possible revenue from making the first cut at 1 foot versus making the first cut at 2 feet versus making the first cut at 3 feet and so forth, we will have figured out, after we've checked all of those possibilities, what the maximum possible revenue is that we can generate from an N-foot piece of rebar. All right, so we're going to return to the general case of having an N-foot long piece of rebar to work with. And within that N-foot length, we'll have K be the position where we're going to make our first cut. We'll just sell the left-hand part for the best price that we can get, and then we'll call a recursive algorithm to try to find the optimal way of cutting up the right-hand remaining part. All right, well, if we have no rebar, we're going to get $0. On the other hand, if we have an N-foot piece of rebar, then the maximum revenue that we can possibly get is going to be the maximum that we can get given where our first cut is made, with that first cut going from 1 feet to N feet. Now, if the first cut is at N feet, that means that we didn't cut the rod at all. The maximum revenue that we can get from making our first cut at K feet is going to be whatever price we can get for that K foot piece, plus the maximum revenue that we can obtain by properly cutting up the N minus K foot remaining piece. You can see that the form of those two equations, where we have the maximum revenue for 0 feet, and then a formula for the maximum revenue for N feet, which will eventually wend its way down to making use of the maximum revenue for 0 feet, those two equations are essentially the same form of recursion that we looked at for computing the factorial function, where 0 factorial was 1, and n factorial was n times the factorial of n minus 1, or for the Fibonacci recursion, where the Fibonacci number for 0 was 0, the Fibonacci number for 1 was 1, and then the Fibonacci number for n was the Fibonacci number for n minus 2 plus the Fibonacci number for n minus 1. So exactly the same structure, but this time we're computing the maximum revenue over a loop on possible positions for the first cut. Okay, so let's look at some specific values of N, that is, specific lengths of rebar that we get from our supplier, and we'll figure out what the maximum revenue that we can get is from chopping that rebar up and selling it to our customers. The top part of slide 40 just repeats our recursive formula, with the little note here that price sub k is going to be 0 except for cuts k in the 1, 2, 3, and 4 foot lengths. All right? So let's suppose that what we get from our supplier is a 1 foot length of rebar. Well, we're going to iterate over all of the possible places that we can make the first cut. In our loop, with k going from 1 to n is 1. So the only place that we can make our first cut is at the end of the 1 foot piece that we have. Therefore, our maximum revenue is going to be the price that we can get for the 1 foot piece, which is $1, plus the price that we can get for the 0 remaining feet, which is $0. Well, the max of $1 is just $1. So the maximum revenue that we can possibly get if our supplier gives us a 1 foot piece of rebar is $1. Let's suppose that our supplier gives us a 2 foot piece of rebar. Now what's the maximum possible value that we can get? Well, again, we're looping, this time k going from 1 to 2. One possibility is that we will make our first cut after 1 foot. So we will be able to get $1 for the 1 foot piece. And we'll have to figure out what the maximum revenue that we can get is from the remaining 1 foot. Actually, we figured that out over here. So if we figure that out again, we'll still get $1. That's $1 plus $1 is the first possibility. The second possibility in our loop is that we make the cut at 2 feet, that is at the end of the 2 foot piece of rebar. We can get $5 for that 2 foot piece of rebar, and of course $0 for the remaining 0 feet. And those are our two possible values of k. We can make our first cut at 1 foot, we can make our first cut at 2 feet. And we can see that the maximum revenue we can get there is $5. Continuing on to looking at a 3 foot piece of rebar that we get from our supplier. Well, now we have to compute the maximum over 3 possible first cuts. The first cut might be at 1 foot or at 2 foot or at 3 feet. And we can simply look up in our price table that we can get $1 for a 1 foot piece, $5 for a 2 foot piece, $8 for a 3 foot piece, and then we would also have to add in the maximum revenue from a 2 foot piece or the maximum revenue from a 1 foot piece in the case of a 2 foot first cut. Or in the case of a 3 foot first cut, we have nothing left, and so we get $0. Now, if we compute the maximum of these 3 possibilities, we see that $8 is the maximum revenue that we can get. And we simply repeat this recipe for figuring out the maximum revenue that we can get from 4 feet, from 5 feet, from 6 feet, from 7 feet, whatever we want that maximum value of n to be. We end up doing more and more and more work, obviously, as n gets larger and larger. So let's take a look at the code that implements this recursive algorithm. Here on slide 43, we have the naive implementation of this recursive rod-cutting algorithm that we've just looked at. By naive, I mean that we have not yet added any memoization. We'll come back to the memoization in a minute. Okay, so the first thing that we have in here is our price lookup. We can sell a 1 foot piece of rebar for $1. We can sell a 2 foot piece of rebar for $5. A 3 foot piece for $8, a 4 foot piece for $9. Now, any other length of rebar our customers won't buy, so we get $0 from anything other than a 1, 2, 3, or 4 foot piece of rebar. We could have set this up as a chain of if, elif, elif, elif for each of these saleable lengths of rebar, 1 feet, 2 feet, 3 feet, 4 feet. I've chosen to use a lookup table here, implemented as a list. So that item sub 1, if we have a 1-foot piece, is $1. Item sub 2, if we have a 2-foot piece, is $5. Item sub 3 is $8. Item sub 4 for a 4-foot piece is $9. And anything outside of that range, anything not greater than or equal to 1 and less than or equal to 4, is always going to give me back a price of 0. Okay, so a lookup table using a list, or perhaps a lookup table using a dictionary, is one way of implementing such a price lookup function. Of course, what really matters here is our maximum revenue function. We're going to start out by creating a variable maxRev that is initially 0. The reason that I'm creating maxRev to be initially 0 is because later on, when I'm looping through all the possible first cuts that I might make, I'm going to want to compute the maximum of the maximum revenue that I've remembered so far, plus the price of a piece cut at k feet, and the maximum revenue for the remaining n minus k feet. If maxRev doesn't exist here, this max function call is going to raise an exception, and my program is going to crash. All right, so let me bring back onto my right-hand screen our algorithm. Okay, so rev n is going to be $0 if n, the length of rebar we get from our supplier, is 0 feet. On the other hand, if n is 1 foot, we know that the maximum revenue we can possibly get is just the price of 1 foot. We only need to worry about looping if n is at least 2. Okay, so if n is at least 2, we're going to loop from 1 foot up to, but not including, n plus 1 feet. All right, so in other words, if n is 2, we're going to loop from 1 up to, but not including 3, 1 and 2, in other words. And our maximum revenue is going to be updated to be the maximum of the maximum revenue we've computed so far, or the price of a k-foot piece plus the maximum revenue from the remaining part. This is simply Python code implementing exactly this statement here. Let's demonstrate that this works. Here is my naive rod cutting program. Same code as on slide 43, but we do have some test cases here. I will run this. And okay, this is interesting. We see that we discovered a couple of ways of getting $25 out of a 10-foot piece of rebar, but apparently it's possible to get $26 as the maximum amount from a 10-foot piece of rebar from our supplier. You can see that this recursive algorithm is slowing down dramatically once we got past about 20 feet. And in fact, I'm sick of waiting for this, so I'm going to press Control-C to kill this off. Let's next smarten up our program by adding memoization to it. Here is the same algorithm, except with memoization added to it in the same way that we added memoization for our factorial function. We start out with a dictionary that's empty, and then for the argument value n, if n, that is the feet of rebar that we get from our supplier, already has a maximum revenue stored in m, we'll simply return whatever that maximum revenue is. Otherwise, we will run our decision and loop. Having computed the maximum revenue that we can get from an n-foot piece of rebar, we're going to save that maximum revenue into our map and then return the maximum revenue. Now, I want to point out, if we go back to our rod cutting examples, Notice on slide 40 that when we were computing the maximum revenue for a 1-foot piece of rebar, we needed to get the maximum revenue for a 0-foot piece of rebar. But actually, we've already computed that, and that's stored in our map. So that does not involve calling another function. We just look up the revenue from 0 in our table. And we memoize the revenue from 1. If n is 2, we look up the price for a 1-foot piece, we look up the price for a 2-foot piece, and we can find Rev 1 and Rev 0 in our dictionary. We don't have to compute Rev 1 or Rev 0. Going on to Rev 3, we're making use of Rev 0, Rev 1, Rev 2, which are in our dictionary, and we're adding Rev 3 to our dictionary. So the performance of this is becoming quadratic now, rather than an exponentially exploding tree of recursive calls. Let's confirm that this version of the code with memoization is dramatically faster than the naive implementation without, even though they will eventually produce the same values. Here's what we got when we ran our naive version. $26 for a 10-foot piece of rebar that we cut up, $40 for a 15-foot piece that we cut up, and so forth. For our memoized version of this algorithm, here I've added even more lengths of rebar that we might get from our supplier. Although, I guess a 100-foot piece of rebar from our supplier would be a little difficult to fit on the truck. But let's see what we get here as far as performance from this implementation that's using memoization. Zip. All right. Good. So we have maximum revenues that we can achieve from lengths of rebar from our supplier, ranging from a 10-foot length up to actually 200-foot length. Okay, so that is one relatively straightforward example of dynamic programming, where we create a recursive solution that solves for every possible combination sort of by brute force, but we organize our recursion in such a way that we can memoize answers to subproblems in a convenient order to dramatically speed up the calculations. Okay, so earlier we looked at breadth-first search, which gave us a way of finding the shortest path from some source node to some target node in a graph. In our example, we assumed that the graph was undirected, that is, you could go either direction from node to node. And we also assumed that there were no weights involved, that is, going from one node to another node just, in effect, had a cost of 1 or a constant cost. Now we would like to look at the problem of finding the shortest path, or what we might call the least expensive path, from every source to every target throughout a graph. Here in the upper left corner on slide 46, we have a representation of a directed, weighted graph involving 4 nodes. The arrow indicates the direction that we can travel in, that is, we can go directly from node 1 to node 4. However, there is no direct connection from node 4 back to node 1. And these red numbers here represent the cost of going from one node to another. Now, that cost might be in dollars, it might be in time, it might be in distance, it doesn't really matter. The point is that it costs us 1 something to get from node 1 to node 4. And it costs us 7 somethings to get from node 4 to node 2, and so forth. As a concrete example, you can imagine these to be different cities that are connected by roads, and perhaps these numbers represent the amount of time it takes in hours to get from one to the other. So we can go directly down a one-way road from city number 1 to city number 4 in 1 hour, but there is no direct node back from city number 4 to city number 1. It takes us 7 hours to get directly from city 4 to city 2, but takes us less time, perhaps there's a higher speed limit, to get from node 2 back to node 4, and so on. We represented our original graph using a dictionary, mapping each node to a list of nodes that were directly connected. But now we have a more complex situation because nodes are not necessarily bidirectionally connected, and we also have to keep track of different costs of going from one node to another. So a common way of representing this kind of information is to use a so-called adjacency matrix, where we have all the nodes in our graph as indexes into rows. We consider those the source nodes. And we likewise have all the nodes in the graph as columns. These are the target nodes, or the 2 nodes. The cells in this adjacency matrix, A sub 0, shows the cost of getting directly from a source node to a corresponding target node. Now, if the cost is 0, that means it's the same node. So there's no cost in getting from node 1 to node 1, or in getting from node 2 to node 2. We're already there in these cases, so the diagonals are filled in with zeros. If no direct connection exists between 2 nodes, we mark that with an infinite weight. So we cannot get directly from node 1 to node 2. Therefore, if 1 is our source and 2 is our target, we're marking that with an infinite symbol. Similarly, we can't get from node 3 directly to node 1. So we have another infinite symbol there. All these other values indicate the cost of getting directly from some source node to some target node. So starting from node 2, it costs us 2 hours to get to node 1 directly. Starting from node 2, it costs us 4 hours to get directly to node 3, and 5 hours to get directly to node 4, and so on. All right, so this initial adjacency matrix, A sub 0, tells us the cost of getting directly from each of the source nodes to each of the target nodes. Our goal is to find the shortest path, or the least expensive path, to get from any source node to any target node, and this is going to require us to also check intermediate connections. So we cannot go directly from node 1 to node 2, but we can go from node 1 through node 4 to node 2. And we can go from node 3 through node 4 to node 2 to node 1. So we want to check all of these possible paths that may involve one or more intermediate nodes and figure out what the shortest or least cost path is from each possible source to each possible target. Well, this sounds very much like a dynamic programming problem. We have a lot of nodes, we have a lot of choices to make in terms of how to get from one node to another. So we need to put some recursive algorithm together that tests all possible sequences of decisions and figures out for each node what the shortest path is to each of the other nodes. All right, so here is a recursive algorithm that computes the shortest path, P of S and T, given some source S and some target T. We know that the shortest path from S to T is going to involve looping or iterating over all of the nodes that are directly connected to the target that we're trying to reach. Okay, so let's pick node 1 and node 3 as an example. If we want to find the shortest path from node 1 to node 3, that's going to be the minimum of the shortest paths through all of the nodes that are directly connected to node 3. All right, node 1 is our source, node 3 is our target. In order to get to node 3, since we can't get there directly from 1, we are necessarily going to have to get there either through node 4 or through node 2, because those 2 nodes are the only nodes that are directly connected to 3. All right, so in other words, we will need to find the shortest path from node 1 to node 4, and then add the weight of going from 4 to 3, we'll also need to find the shortest path from node 1 to node 2 and add the weight of going from node 2 to node 3, and we'll take the minimum of those two possible values. Okay, so that gets us the shortest path from node 1 to node 3. We need to try all possible combinations. Now, it should be clear that each node is allowed to appear in a path at most once. If we did have a path in which a given node appeared multiple times, that would imply that we have a cycle in our path, and a path containing a cycle can't be shorter than a path not containing the cycle. All right, so for our given target node, which was 3 in our example, we're going to have to test all of the directly connected nodes, in this case node 2 and node 4. It really doesn't matter what order we do that in. So we're going to just arbitrarily pick one first and the other one second and go through each of the possibilities. Okay, so our complete recursive formula is that the cost of going from any source to itself is 0. We don't need to worry about those diagonals at all. And then for any source and target that are not the same, we can find the shortest path from each source to each target using our minimization algorithm. Now, when we did our Fibonacci number computation, our original naive recursive algorithm was exponential and blew up very fast. But using memoization, we were able to modify the algorithm so that each time we incremented n by 1, we only had to calculate one more number. And consequently, we were able to get an order n algorithm for Fibonacci numbers, much better than exponential. For the rod cutting algorithm, it was also the case that our naive recursive algorithm was exponential, but we were able to find a polynomial time algorithm through memoization. Here, in this problem, we have n source nodes, and we have to compute a minimum cost to get to each of n target nodes. So before we even begin, our algorithm is at least n squared. But by using memoization, we'll discover that we only need to create a list of n adjacency matrices rather than an exponential tree of such matrices. And so we'll find when we're done here that we have an order n cubed algorithm. All right, let's see how this goes. A sub 0 is our adjacency matrix. We can think of A sub 0 as being a shortest path matrix where 0 intermediate nodes are permitted. That is, we're only allowing direct connections. We're going to try adding additional potential intermediate nodes in label order. We have to try all of them, so we'll just, for convenience, do intermediate node 1 first, and then add the possibility of intermediate node 2 next, and so on. A sub k is going to be a matrix containing the shortest possible paths from each source to each target, where we're allowing nodes 1 through k as potential intermediate nodes. That is, here's A sub 0 where we're allowing 0 intermediate nodes. A sub 1 is going to be our shortest path matrix where we allow 1 as the only possible intermediate node. A sub 2 then will be the shortest path matrix where we're allowing 1 and 2 as possible intermediate nodes. And as we step through this, eventually we'll be able to use 1 and or 2 and or 3 and or 4 as possible intermediate nodes. And of course that will exhaust our possible intermediate nodes. We will end up with A sub 4 containing all shortest paths using any of the 4 nodes as a potential intermediate node. Let's take a look at A sub 1 as a specific example and then come back and talk about this red formula here on slide 50. So here on slide 51, we have A sub 0, which is our original adjacency matrix. we can think of A sub 0 as being the shortest paths from each source to each target where only direct connections are permitted. Now, traveling from a source to itself is always 0, so we're always going to have zeros on the diagonal. If we don't have a direct connection, then we have infinity as our cost, so we don't have a direct connection from 1 to 2. And otherwise, we have these weight values. So getting from source 2 directly to target 1 without any intermediate nodes costs us 2. We're going to construct A1 from the information in the A sub 0 matrix. Now, A sub 1 tells us the length of the shortest path that we can use to get from each of the source nodes to each of the target nodes, where now we're permitted to use node 1 as an intermediate step. All right, A sub 0 is direct connections. A sub 1 is connections where we're allowed to use node 1 as an intermediate step. Now, we can't have cycles. That is, we can't improve anything starting from node 1 by going through node 1 a second time. So the entire first row here, where 1 is the source, can't possibly change by going through node 1 again. Similarly, the column where 1 is the target can't possibly change for the same reason. The diagonal is always 0, as I said, because here each source is its own target. So the only cells that we might change by discovering a shorter path are these 6 cells that are off the diagonal and that are not in row 1 or in column 1. So let's take a look at these. What is the shortest path from node 2 to node 3 if we are now allowed to consider an intermediate step through node 1? Well, the shortest path from node 2 to node 3, if we're allowed to use node 1 as an intermediate step, is going to be the shortest path that we currently already know from the adjacency matrix, A sub 0, 2, 3. All right, A sub 0, 2, 3 is 4 because the direct connection from 2 to 3 has a cost of 4. The other possibility is that we could use 1 as an intermediate node. We could go from our source of 2 to the intermediate node 1, and then from node 1 to the target node 3. The sum of those two costs might turn out to be less than the cost of going directly from node 2 to node 3. Let's see whether that's the case. So the cost of going directly from node 2 to node 3, we already know is 4. We can just read that out of A0. The cost of going from node 2 to node 3 indirectly through node 1 is the cost of going from node 2 to node 1 plus the cost of going from node 1 to node 3. Well, going from node 2 to node 1 costs 2, but going from node 1 to node 3 is infinite. There is no connection directly from node 1 to node 3. So we end up here with 2 plus infinity. Obviously, the minimum there is still 4. So we did not find a shorter path from node 2 to node 3 by using node 1 as an intermediate node. Well, let's try going from node 2 to node 4. Going from node 2 to node 4 directly costs us 5. All right, so one possibility is that I can use this lowest cost that I know about so far, A sub 0 sub 2 comma 4 is 5. Or I could try using node 1 as an intermediate step. I could say, give me the cost A sub 0 2 comma 1 plus A sub 0 1 comma 4 this time. All right, well 2 comma 1 we already know is 2. 1 comma 4 is 1. So that turns out to be 2 plus 1 is a 3, which is less than the 5, which is the shortest path that we knew from direct connections. So this cell gets filled in with a 3. That is, we have found a shorter path from node 2 to node 4 by using node 1 as an intermediate node. Let's see if that makes sense. So we're going from node 2 to node 4. We see that there is a direct route that costs us 5 hours, if these are towns. However, if we go from 2 to 1 to 4, that's only going to take 3 hours. All right, so that's an improvement. Now, the remaining 4 things that might possibly change don't change. There is no direct connection from 3 to 1 or from 4 to 1, so using 1 as an intermediate node cannot help us find a shorter path from 3 to anything else or from 4 to anything else. Okay, so we started with our 4x4 adjacency matrix A sub 0, and using information from that, we have built another 4x4 shortest path matrix in which node 1 is allowed to be an intermediate node. Okay, so if we now take a look back at this messy formula here on slide 50, what we're saying is that in the matrix A sub k, where nodes 1, 2, etc., up to k are permitted as intermediate nodes, the value in a given source comma target slot in the A sub k matrix is going to be the minimum of the value from the A sub k minus 1 matrix that we already know, or the sum of going from S to k in A sub k minus 1 plus going from k to t from A sub k minus 1. See, this is what we had over here. The cost in A sub 1 of going from 2 to 3 was the minimum of that same cell value from A sub 0, or the sum of the cell values where we're using node 1 as an intermediate node between node 2 and node 3. All right, so that's what this messy formula means. Let's take a look next at A sub 2. Okay, so here on slide 52 on the left-hand side is A sub 2. A sub 2 is going to be the shortest paths from the source nodes to the target nodes, either because the nodes are the same, that is, the diagonals remain 0, or using a direct connection, or using node 1 as an intermediate node, and now also or using node 2 as an intermediate node. So we're going to construct A sub 2 out of information in A sub 1. Fortunately, we don't have to look back at A sub 0. We can get everything we need from A sub 1. For example, here, A sub 2, 1, 3, that is A sub 2 with 1 as a source and 3 as a target, is either going to be the shortest path that we already knew about from A sub 1, or it's going to be A sub 1 with 1 as the source, now allowing 2 as a possible intermediate node, plus A sub 1 from 2 to 3. Okay, so either the shortest path that we already know, possibly using node 1, or the path from 1 to 3 using node 2 as an intermediate node. Now, in this particular case, A sub 1 of 1, 3 is infinite. We certainly can't do worse than that. A sub 1 sub 2 is also infinite, unfortunately. So what we're going to compute here is the minimum of infinity or infinity plus something. And so in A sub 2, we still have not found a short path from source 1 to target 3, either directly or by using node 1 or by using node 2 as an intermediate node. Now, for the same reasons that we talked about in A sub 1, the row with 2 as a source and the column with 2 as a target cannot be changed in A sub 2. Because if something in the row were changed or if something in the column were changed, that would imply that item sub 2 is appearing twice in the path, and we're not allowed to have cycles. So the only values in A sub 2 that could possibly change, again, are these values that are off the diagonal and that are not part of row 2 or column 2, that is these green cells. And it turns out that the only one that does actually change is using 4 as our source and 1 as our target. Let's see how that works. All right, so to compute A sub 2, 4 comma 1, that's going to be the minimum of A sub 1, 4 comma 1. All right, well, A sub 1, 4 comma 1 is infinite. We can't do worse than that. Or the sum of A sub 1, 4 comma 2 plus A sub 1, 2 comma 1. All right, we're going from 4 to 1 using node 2 as an intermediate. Fortunately for us, that's going to help. So we go from node 4 to node 2. It takes us 7 hours to get from node 4 to node 2. And then we can get from node 2 to node 1 in 2 hours. Okay, so now instead of not knowing about any connection between node 4 and node 1, since we're allowed to use node 2 as an intermediate node, we now have a connection that takes us 9 hours. So we're able to fill in A sub 2, 4 comma 1, with 9 rather than the infinity we had back in A1. A sub 3 is going to additionally allow us to use node 3 as an intermediate node. To be clear, in A sub 3, we have either the same node as the source and the target, so the diagonal is always 0. We have direct connections permitted. We also now are able to use node 1 as an intermediate node, and or node 2 as an intermediate node, and or node 3 as an intermediate node. But unfortunately, as we step through our computations here, we discover that being allowed to use node 3 also as an intermediate node does not give us any improvement. So A sub 3 ends up being the same as A sub 2. We have not discovered any new shorter paths. Finally, we get to A sub 4. Here's A sub 4. Now, if the source and target are the same, it's still 0. And now the shortest path may be a direct connection, or it may involve node 1 as an intermediate node, or it may also involve node 2 as an intermediate node, or it may also involve node 3 as an intermediate node, and it may even involve node 4 as an intermediate node. Now, so we've used up all the cases. There can't be any even shorter paths because we've used up nodes 1, 2, 3, and 4 as possible intermediate nodes. And so if we attempted looking for even shorter paths, we would necessarily start creating cycles. Okay, so in A4, row 4 and column 4 cannot be different from what they were in A sub 3. The only values that might conceivably change are these values in green that are off the diagonal, not part of row 4, not part of column 4. Let's take a look at going from node 1 to node 3 now that we're allowed to use node 4 as an intermediate node. Okay, so going from node 1 to node 3 is either the shortest path that we had so far discovered in A sub 3. Well, that's not very helpful. That's infinite. So hopefully we're going to be able to do something better than that. So either it's infinite or it's A sub 3 going from node 1 to 4 plus A sub 3 going from node 4 to 3. So in other words, we're getting from node 1 to node 3 intermediately through node 4. Well, let's see. A sub 3, 1, 4 is 1. A sub 3, 4, 3 is 1. Cool. So 1 plus 1 gives me a 2. 2 is definitely better than infinite. So now I have discovered that I can get from node 1 to node 3 with a cost of 2, that is 2 hours. Let's see how that works. We go from 1 to 4 in an hour and from 4 to 3 in an hour. And so we have made it from node 1 to node 3 in 2 hours. Okay, so because this graph is a single connected component, it turns out that in A sub 4, we don't have any infinities remaining. If we got to A sub 4 and discovered that we still had some infinities remaining in our matrix, that would imply, because we have checked all possible intermediate nodes, that there simply is no possible connection between one node and another. But that's not the case here. All of the nodes are eventually connected in some way. And A sub 4 contains the lengths of the shortest paths between all source and target pairs. All right, so that's it. Now I have created these slides 54, 55, 56, 57 for your own use if you're interested in tracing through the steps starting from the adjacency matrix A sub 0 to get yourself all the way to the ultimate shortest path matrix A sub 4 to make sure that you understand the various steps. We started out with our weighted directed graph represented by a 4x4 adjacency matrix, and we ended up creating 4 4x4 shortest path matrices in order to get to the ultimate shortest path matrix, allowing any of the 4 nodes to be used as intermediate nodes. In other words, we created 4 cubed cells in these matrices, and it should be easy to see that we have an n-cubed algorithm if we have n nodes in our graph. Alrighty, so that is that.